Mamma mia, welcome to this new video. On that circuit on the board, the switch in the circuit has been closed for a long time and is open at T equal to 0. Find the voltage across the capacitor after 500 milliseconds. So we discover that before we close the switch, we know that at T less than 0, the switch is closed. And if the switch is closed, the voltage across the capacitor is equal to 0 due to GCE circuit, knowing that IC, the current flowing through the capacitor, is equal to C, derivative of VC and T. And if VC is equal to a constant, this implies that IC will be equal to 0. And if we set it like that, we discover that we can have, before we close the switch, we will have this voltage source plus minus and here is 3 ohms, here 9 ohms, and here 1 ohms, and here is the voltage VC. Now, according to what we saw in the ohm voltage divider V 20 ohms, we discover that as we have here an open source, the VC will be appearing here. And now by applying voltage divider, we are going to have VC is equal to 9 times 20 divided by 9 plus 3. And if you perform this operation, we are going to have VC equal to 15 volt. Means that before we close the switch, means that at T greater than 0, the initial voltage across the capacitor is equal to VC equal to VC0, which is V0 is equal to 15 volt. That is it. That is the initial voltage across the capacitor. Now, when we open the switch at T equal to 0, means that a few moments after we open the switch, the circuit diagram will be different. When we open the switch, now the switch is open. Let me draw another diagram so that we will understand it very well. We will have here the switch is open like this. I'm not taking that other branch in consideration. We are going to have something like that, and here is C, here is 1 ohms, and here 9 ohms, knowing that this point is the reference of the voltage. We are not taking this switch in consideration. We discover that here VC here now will be different. VC now will be an exponential evolution in terms of time. We can now transform this circuit in order to have an array equivalent and a capacitor all in parallel. And here we have VC. When we have it like that, we discover that the voltage VC is going up, means that the current going through is like that, and it's the same current going like that. And if that current is going up like that, means that also the voltage is going down. Now if you apply now the second law of Kirchhoff in this small circuit, means that you launch a loop here like that. We are going to have VR plus VC equal to 0, and VR himself is equal to I, which is here IC time R equivalent plus VC equal to 0, and I alone is equal to IC is equal to C, derivative of VC in terms of T. Now let us take the expression of this current and come and substitute in this other element and see what we can have. When we have it like that, we are going to have that expression like this, R equivalent time C, derivative of VC in terms of T plus VC equal to 0. We discover that you have a first order differential equation, and to solve this equation is very simple and fun to solve. I'm going to arrange the term in order to have something very simple. We have a derivative of VC on VC plus I will take this other item and come and send it down here and arrange it very well. Derivative of VC plus 1 on R equivalent C time V d of t will be equal to 0. Now when we reach here, now you can say that derivative of VC on VC equal to negative 1 on R equivalent C time d of t. Now if you introduce the integral in both sides, we are going to obtain ln of VC will be equal to 1 on R equivalent C negative time t. Now in order to get only VC alone, I'm going to compose in both sides by exponential. Now when you compose in both sides by exponential, we are going to have VC of t equal to exponential negative 1 on R equivalent C time t plus a constant k. Let's say we will not have that constant k because that constant was here, but it was a constant k. And here that constant is supposed to be up there plus c. Once we have it like this, we discover that when you have exponential of a plus b is equal to exponential of a times exponential of b. This is a recall. When you have exponential a plus b, this will be equal to exponential a times exponential of b. Now if you apply that formula in this expression, we are going to have a VC of t equal to exponential negative 1 on R equivalent C time t times exponential of a constant c, and that constant c will be defined as initial voltage of the capacitor VC0. Now when you arrange it very well again, we are going to have VC of t equal to V0 exponentiellement 1 on R equivalent C time t. Knowing that here we always take constant of charge, which is here tau equal to R equivalent time c. So we can simply say VC of t is equal to V0, which is the initial voltage of the capacitor, minus exponential minus 1 on tau time t. So that is the expression of the voltage across the capacitor. Now if we replace all the value by their respective value, we are going to have a VC of t, knowing that V0 was 15 volt exponential minus 1 on, when you perform the expression of t, we are of tau R equivalent times c, we are going to have let me see, 0.2 second, means that we are going to have 0.2 time t. Okay, that is the expression of the voltage across the capacitor after 500 milliseconds. Now in the same way, we can perform the initial energy storage by the capacitor. The initial energy storage by the capacitor, we know that the energy storage by inside the capacitor W is equal to 1 on 2 C time VC 0 square. Keep mind in that formula, that is the value of the energy storage inside the capacitor, and if you have like that, that will be looking like that. So the capacitor here, the value of the capacitor here is 20 nanofarad. When you perform it, you are going to have the initial energy inside the capacitor equal to 1 on 2 times C, 20 nanofarad, a millifarad, which is 20 times 10 negative 3 times VC0 here was 15 volt square. Now when you perform this operation very well, you are going to have the initial energy inside the capacitor, which is equal to 2.25 watts. That is all about that exercise. So if you have a question, don't forget to ask in the description section below. I will be very happy to answer that question for you. And if you are new in this channel, don't forget to subscribe so that you will not lose the incoming video. Switching guard for watching. Peace.